Hey everybody, welcome back to another round of physics, and yeah, let's get going. For you today, I have prepared a couple of example problems that we can get some practice applying Kirchhoff's current law, Kirchhoff's voltage law to analyze circuits. So for you, here we go. We have a circuit. Go ahead, run through the checklist. Think about what are the things that I need to do in order to get this problem set up and to get my equations using KVL, KCL. Yeah, you got it? Okay, so I'll go ahead and run through with us now. Since you've already done the work, now we'll just check it. So of course, first off, we should think about drawing the circuit. And here I have already got it drawn in a manner that seems a little straightforward, or that I don't think this presents any additional complexities in terms of visualization. So we'll just leave that as is. But the next step is that we should be thinking about the currents in each of the individual branches. So I'll go ahead and arbitrarily choose some current directions. So from the 3-volt battery, let's say that there's current flowing through the 3-volt battery going from the right to the left. And I'll go ahead and label that I1. Notice that the 1 ohm resistor is in series with the 3-volt battery. And so I'll just subscript that as 1, thinking about the resistor. For the 12-volt battery, yeah, well, let's go ahead and say that it's going this way. So I'll call that I12. From right to left again. And why not? Let's go ahead and say that the current is flowing this way through the 6 ohm resistor. So again, I'm going to label that as 6. Okay? So now we have arbitrarily chosen our current directions. And yes, you might be screaming and kicking, but I have indeed chosen some to ensure that we get some negative currents after we go through our analysis. Okay? Well, the next step, let's go ahead and label the high and low potential sides of all of the circuit elements. Of course, the batteries are easy. Those automatically are chosen for us based on the low, the short bar, and the long bar. Now, the drops and jumps across the resistors are all based on the directions that we chose for the currents. And since I have it going from left to right across the 6 ohm resistor, the left-hand side represents the high potential. The right-hand side represents the low. Similarly, across the 1 ohm resistor, you can think of I1 must be going this way, right, through that part of the circuit. And so the right-hand side is the high potential. The left-hand side is the low potential. And we're done. We have labeled our high and low sides. Next up, we should be thinking about the number of unknowns. Of course, considering that I've already drawn in the circuits, or the currents, we basically have 3 unknowns. And by knowing 3 unknowns, we know that we have to find 3 equations. So let's go ahead and apply KCL. So I should be thinking about, okay, how many junctions do I have? And we see that there are 2 junctions in this circuit, 2 places where wires split and or combine. And here I'll go ahead. I generally use letters to label my junctions so that we don't confuse them with, say, resistor values or battery values, etc., etc. Now, without loss of generality, I'll go ahead and analyze junction A. You can pause the video and go ahead and write out the Kirchhoff's current law for either junction, and I guarantee you'll get the same expression for this example problem. Okay? Now we recall that the current law says that the amount of current going into a particular junction or node is equal to the current that comes out. So if I look at junction A, I see that I1 and I12 are both going into that junction, and coming out is I6. And I'm done. That's all there is to that. Next up, we have 2 more equations that we need to find. We have additional 2 unknowns, and so we will have to choose two loops or paths around the circuit to analyze. Now, you should stop and ask yourself, how many paths are there? Good. There's three. Okay. You could take the top loop. You could take the bottom loop. Maybe I shouldn't say top and bottom. You could take the top path. You could take the bottom path. Or you could take, say, for lack of a better word, you have the outside. Okay. So you have the top, you have the bottom, or you have the entire outside path. And that's it. Okay. We just need to choose two of the three. Okay. Let's see here. For complexity, I'm going to take the top path, and I'm going to take the outside path. Okay. Now, I say complexity because the bottom path, basically, we could find a result straight off, okay, without subbing and solving. And I thought, well, we should at least do a problem where we have to sub and solve and kind of work our way through. So I'll go ahead and take the top path, and the direction that I walk should not affect the problem. So I'll start at A, and let's pretend that I'm going to go, no, that's clockwise. I'll go clockwise around that top path. So I'm starting at A, I walk, and I should notice here, the sum of the jumps should equal the sum of the drops. So you can imagine starting at A, walk, and across the 3-volt battery, you notice that you have a drop. Okay. So I'll put that on the drop side, I'll say V3. Okay. And we keep going, and here, based on our labels, you notice that the resistor, it represents a jump. I go from the low to the high potential side. So I'll put that on the jump side. And I'll keep walking, I'll walk, and I get to the 12-volt battery, and again, I move from the low to the high side. So that is a jump. And I finally arrive back at position A. Now I'll go ahead. Let's go ahead and substitute in expressions. Because I'm dealing with the potential drop across the resistor, I can think about replacing that with Ohm's law. Okay. And so I can take that potential and express it in terms of the current I1. So I'll go ahead and write that. We have I1 times, well, we might as well put it in. I'll go ahead and put in 1, the resistance value. Of course, the battery, the potential is 12, and here we have a potential of 3. In my efforts to avoid subbing and solving, I picked a path that doesn't need any sub and solve. Oh well, okay, trash that. And we can see right away that I1 must be equal to -9, and we have to be careful here. Right, we have volts, and an ohm. And so this ends up being an amp. Volts divided by ohms is amps. So we get -9. Well, let's go ahead and do the outside loop next. Okay? And here I'm 100% positive that we will not be able to actually solve it straight off. So we have, this is the top loop. Here we'll do the outside. And let's go ahead and walk counterclockwise around this one. So again, I'm thinking the sum of the jumps should equal the sum of the drops. And so we'll go ahead. Let's start, well, yeah, why not, at A, and I'll walk clockwise. And across the 6 ohm resistor, we notice that we have a drop. So I'll put V6 here on the right-hand side of my equal sign. I keep going, go, and I get to the 1 ohm resistor, and again, we notice that that represents a drop. So I'll add to that the potential drop across the 1 ohm resistor. I keep going, and I cross the 3-volt battery, which represents a jump. So on this side, the 3-volt battery, and I keep going, and I'm back to my original starting location. So we're done. I'll again use Ohm's law. Here we have 3 volts, that's just the battery value. I have the current going through the 6 ohm resistor times 6 ohms, plus the current going through the 1 ohm resistor times 1 ohm. Okay. And here is some place where I need to emphasize again. I said we arbitrarily chose our directions for the currents, and we notice that the current flowing through the 1 ohm resistor is negative. Okay? Do not change your figure right now. Okay? One of the tendencies is to see that this is negative and to immediately erase that current and draw it the opposite direction. I1. Okay? Oh, let me fix it right now. Okay? No, because don't forget what we labeled as high and low sides on the resistor was predicated on the direction initially chosen for the current, which means that our current law and our loop rules are drawn based on this value, that direction of the drop or the jump. Okay? Do not change it midway. You get a negative value, that's fine. Solve the entire circuit before you worry about those negative values. Okay? Why I say that is that you notice on our second equation that we've gotten applying Kirchhoff's voltage law, I can take I1 and I can substitute it in. Let me get rid of that. Okay. And I want to substitute in the negative value. Okay. So here, what we get, smaller arrow, we get a 3 equals 6I6 minus 9. Okay? And now we see that we can solve for I6. I've substituted in, I can solve for I6, move the 9 over to the other side. I get 12 is equal to 6I6, or that I6 is equal to 2 amps. Okay. And notice the positive sign, we initially guessed the correct direction for the flow of I6. Okay. That's all that positive sign means. We happen to draw that arrow correctly. Well, if we want the current I12 now, we need to take these two currents and substitute them into our KCL expression. Well, I'll go ahead and flip to a new page. There's no reason to try to cram everything in here. So we're back at KCL. And from that, we had I1 plus I12 is equal to I6. And for I1, we got negative 9. And for I6, we had 2. And so at the end of the day, we find that the current coming from the 12-volt battery must be 11 amps. Again, notice the presence of the positive sign. And we're done. We have officially solved the circuit for everything that's needed. Okay. Notice there are 2 batteries in there. That doesn't slow me down. The fact that there's 2 batteries, I still should be able to apply KCL, KVL to find an answer. Okay. Now that we have the whole circuit solved, now's the time where if you want to redraw the circuit, notice redraw, not draw on top of the previous one, not erase stuff and relabel. Okay, I will redraw it, and now we know that, well, the current flowing through resistor 1, the 1 ohm resistor, I originally had chosen it going counterclockwise. It is actually going clockwise, and it of a value of 9 amps. I almost put volts there. Of course, the current flowing through the 12-volt battery, we had that initially in the correct direction, and that's 11 amps. And of course, the current flowing through the 6 ohm resistor, we found that to be 2 amps. Okay. I guess if you want, you can relabel all of this, put that in there. This raises another point, and you notice that this is a little hard to look at. Okay. I would encourage you, when you're doing this, feel free. I think that it's really useful to have separate colors for different things that I'm dealing with in the circuit. So maybe having green for your currents, that just helps distinguish some of the stuff that you've drawn on top of the circuit from the actual circuit elements. So I would encourage you to make liberal use of separate colors, particularly if, go out and buy a set of colored pencils, or if you have a tablet and do your work on a tablet. Usually it's really helpful to do, say, the currents in different colors, or maybe you do the high and low potentials in a different color than the circuit, which is a different color than the currents. Okay, those kind of things. But that is also a nice organizational technique, so that you can visually kind of use your eyes to distinguish different parts of the circuit. Good? Awesome. Okay, well, let's go ahead and do another circuit. So here I have one, and I just pulled this straight from the book. I think this is problem 2612 from the book, but you can make up your own circuit and just go at it. Okay, it's pretty hard to build a circuit that's not physically possible. I can think of a couple, but it's pretty hard not to. Or it's pretty hard, yeah. Okay. Now here you notice, rather than giving the potential across the battery, this problem actually tells us the current flowing through the 6 ohm resistor. Okay. So first off, go ahead, take a minute, label currents, the high and low sides for this circuit. Got it? Okay, good. Well, I'll go ahead. Let me say that the current through the battery, I'm just going to label this IV. Okay. So there's that for that bottom branch. For loss, arbitrarily, I'll call this one I20. Of course, I6 is already given. I'll go ahead and say that I8 also flows from left to right, similar to what I6 does, I8. And frankly, although we could do it, it'd be pretty silly to say that the rest of the current's going this way, right, through I25. Right, I mean, I think that would make sense. Like, there are good choices. You might as well make your life a little easier if you can. But if I6 is going from left to right and I8 is going from left to right, it makes sense that the current flowing through that 25 ohm resistor would be also going from left to right. Okay, why choose a direction that we know will result in a negative sign? Good? So the next thing, let's go ahead and label the high and low sides of the circuit. And as commented, I'll go ahead and do this in a darker blue. So battery is already taken care of, and I6 is already taken care of. There we go. I8, well, yeah, from left high to right low. And the same thing for I25. Left side is high, the right side is low. And the same thing for I20. So we'll do that. Now, we should make sure we know how many unknowns we have. And that's a little straightforward now because I've done them all in cyan. And you notice that we have 1, 2, 3, 4 currents that are unknown. So there's 4 I's. And the last thing we pick up on is that, well, our battery potential is also unknown. Okay. More often than not, it'll just be the currents are unknown and the battery potentials are known. But here, I just chose a problem where V isn't given. It's perfectly fine. Okay. So we have 5 unknowns at the end of the day. So we are going to have to find 5 equations. Okay. So let's go ahead. Next thing is I want to apply KCL as often as possible, partially because the equations are just more, the resistors aren't in there. So there's less numbers, there's less stuff in those equations. And when we apply KCL, we have to find our junctions, places where the wires split or come together. Okay. Now, we have to be a wee bit careful here because we might be tempted, if I go through and start labeling, I have A right here. You could think, oh, well, I have another split here, B, and then another split here. I'll call that one C, and then we have D right over here. Okay? And we have to be a wee bit careful. If I think about the potential at location A, and I compare it to the potential at location B, okay, how do those two compare? Yeah, good. You notice that these are actually equal. Right? The potential is the same. Okay. Yeah, because these two are at the same potential, they're connected by a perfect wire. There's no change or drop or anything like that. You could think, let's take that perfect wire that's located right here, right? You could actually think about shrinking that wire down so that the junction of A and B are the same. In fact, maybe I'll redraw it here just so that we can see what that looks like. You could think, get into that junction, and basically I have three choices, right? This is a completely equivalent way of drawing this circuit. Here's the 20 ohm resistor. Here is the 8 ohm resistor. Here is the 6 ohm resistor. Okay. Now notice the 6 and 8 ohm resistor combine to go to the 25 ohm resistor. And then the 25 ohm resistor and the 20 ohm resistor end up combining and coming back. Okay. And drawing it this way, we can see that A and B now, that whole place, that's right here. That's that green node. Okay. And then we have a second one here. We have a third one there. So we actually only have 3 junctions. Okay. And because we only have 3 junctions, we can apply KCL twice. So just be careful, right? When you have a perfect wire connecting 2 branches, you can basically think about getting rid of that wire, and those 2 branches are connected at the same location. Okay. So I say all of that to say, for lack of a better term, I'm going to get rid of that label for B. It's all a single junction. Okay, good. Pause the video, convince yourself that that's okay. So let's go ahead. We'll apply KCL. I don't know, fielder's choice. I'm going to go ahead and I will apply KCL to junction A, and I'll apply it to junction, I don't know, D. Good? Okay. So go ahead, take a stab at junction A. I'll go back to the dark purple. Let's go ahead, take a stab at junction A, thinking about the currents in are equal to the currents out. Okay, good. Well, junction A, we have the IV, the current running through the battery is going into that junction. We see that I-20 is going out, I-20. And now we have to remember, oh yeah, this is a perfect wire here. And so we have I6 and I8 also coming out of that junction. So we have I6 and I8. Okay. And there is one of our equations. Okay, so I'll label that equation 1. How about junction D, delta? And no, at some point, it's always good to state the initial equation. Considering of how I've set this up, my initial equation's here, and now I'm going to apply it to junction A. You don't have to rewrite it as long as it's visually close or organized on your piece of paper. Okay, so yeah, if you went to a new piece of paper, it's probably a good idea to put the general equation back at the top. But here, if I'm looking at junction D, we see that I-25 is coming in, and I-20. Right, from this middle branch, for lack of a better word. And then coming out, well, we follow along and we go, yeah, that's still IV. So going out is IV. Okay. And I'll go ahead and call that equation 2. Now, because we argued we had 3 junctions, we can use at most 2 of them. we have, and that's all we can do here. Okay, so that's it. So we are stuck now using the loop rule, KVL, for the other three equations. So go ahead. Find a couple loops. Go ahead, write them down. We'll probably choose different ones. That's perfectly fine. You got it? Okay. Good. Good. And you can notice I can see at least 4 loops here. Maybe there's 5. Okay. Of course, you can think of, well, we have this bottom one, okay, right here. You can think of, I have this middle one. I have, for lack of a better term, I'll say this top one that involves the 6 and the 8 ohm resistor. And then I have some other combinations, like you could imagine the loop containing the 20 ohm resistor, the 6 ohm resistor, and the 25 ohm resistor. Or you could think of the loop, the loop containing the 6 ohm resistor, the 25 ohm resistor, the 20 ohm resistor. Or you could think of the loop with the 20 ohm resistor, the 8 ohm resistor, the 25 ohm resistor, like that. Okay. Or you could do the bottom battery and yada yada. So there's probably 6 or 8 different loops here. Okay. I'm only going to draw in 3, okay, just for sake of not, messing up our figure too much. So it's good to at least indicate which loops you're going to use on the figure itself. So I'll go ahead. I'm going to think about using the bottom loop, and I'll go ahead and go clockwise around the bottom loop. So I'm going to use the bottom. Okay. I'm going to use this 8 ohm, 6 ohm loop just to make my life easy. So I'll call it the top, for lack of a better word, I'll call it the top loop. And why don't we go ahead and use, I don't know. I'm just thinking about loops that make my life easy. I'll go ahead and let's use the full outside loop. So by that I mean the battery coupled with the 6 ohm resistor, the 25 ohm resistor. Okay. And some of these choices, as you get more and more familiar with applying Kirchhoff's laws, you'll notice that some choices are really nice, some of them are less so. Here I've tried to include loops that contain as much of the known information as possible. In other words, the 6 ohm resistor. Whew. Well then, let's go ahead. I will go ahead and apply KVL to the bottom loop, the top loop, and the outside loop. So we remember that KVL is the sum of the, pen color. The sum of the drops is equal to the sum of the jumps. So for the bottom loop, you can imagine, I'll go ahead and start here at location A. And the 20 ohm resistor represents a drop. Okay. Now, I've been in the past just writing VR20, just to remind ourselves this is a potential drop. But it is common to, rather than write this in, it is common to just immediately substitute in Ohm's law. In other words, I20 times the resistor value of 20 ohms. Okay. I'll keep walking. I get down and I have a battery. The battery representing a jump. So I'll just put V battery, or well, V, I guess I have it labeled as V. And that is the bottom loop. Done. Well, let's go ahead. The top, again, I'll just, for consistency, I'll go ahead and just go clockwise again. And we see that I move from the high potential side to the low potential side of the 6 ohm resistor, and that represents a drop. So I have the current I6 times 6 ohms. And I keep going, and we notice that for the 8 ohm resistor, I move from low to high, and that represents a jump. So I have I8 times the 8 ohm resistor. And lastly, I said the outside. So I'll go ahead, I'll start at location A, and I go across the 6 ohm resistor representing a drop. So I have I6 times 6. Keep going. I go across the 25 ohm resistor, which represents a drop. So I have the current going through the 25 ohm resistor times 25. And I keep going, and I hit the battery, which represents a jump. And now we notice that we have 5 equations and 5 unknowns. I should be able to solve this system of equations for the unknowns. At this point, physics is done, math has taken over. Now, that's not to say the math isn't important, and yes, you need to know how to do it in a manner that's consistent, that you get the right results. But this is probably the part that takes more time and is less less insightful from a physics standpoint. Okay, so math is taken over. Okay? If we look at this, we go, sub and solve, yada yada yada. Let's focus in on equation 4 for a moment. And the reason I'm focusing in on equation 4 is let us not forget that we actually have the current going through the 6 ohm resistor. That was given in our problem. So looking at equation 4, we have that 4 amps times our 6 ohms is equal to the current flowing through resistor 8 times 8 ohms. And so we immediately can solve equation 4 for the current. It must be, well, 4 times 6 is 24, divided by 8. Good. It's 3 amps. Well, let me... Yay? Yeah, good. So right away, we know that the 8 ohm current, the current going through the 8 ohm resistor is equal to 3 amps. Well, that basically means I've used this equation. It's always good to keep track of which equations you've used and solved and that kind of stuff. So this one's taken care of. Okay. Now, let me get my bearings about me. Are there any others like that? 20 and V. Oh, we have the 6, but we have a 25 and a V, so I don't know. I have 2 unknowns in there. Of course, you have those 2 I do know. Here's one that I don't know. Here's one that I don't know. It's always good to just sit back and look at all the equations. Don't know, don't know, don't know. Okay, good. So there's not any other equation that's really simple like that, right? Like oh, there's only one known. I can go ahead and sub and solve. Okay, now we have to sit back and kind of look and kind of finagle the equations in our head. And this is, you're going to make mistakes on this. Sometimes you're going to start down a path and you're going to find out, oh, wait a minute, that's not quite the right sub and solve. Okay, that's only natural. In fact, I did it myself and I just cut it out of the video for sake of time. Okay, not because I'm ashamed that I made the mistake or that I kind of went down a rabbit hole, but rather for sake of your time and honoring, like you don't want to have 10 minutes of a video that leads you in the wrong direction. Okay, so please be aware I make these mistakes too, especially with the sub and solve procedure. So the first thing I notice now is I'm looking at equations 3 and 5. And what I want to do is I was thinking, is there some unknown that I can sub and solve to get rid of? And the first thing I noticed is that both equations 3 and 5 can be combined to get rid of V, the potential of the battery. So if I think about that, if I take 3 and 5, okay, subbing those 2 equations together, I get something that says, well, we already know the value of the current for 6, so I get 24 plus I25, again, times the 25 ohm resistor equals the 20 ohm resistor times the current going through the 20 ohm resistor. Okay? Now that in itself, you say, well, it seems like you haven't done anything. It seems like you haven't made any progress. And I would, for the most part, agree. Okay? So I haven't made any progress yet. Okay? I've gotten I25 and I20 together. Okay? The second thing that I'm going to look at is equations 1 and 2. And in equations 1 and 2, I notice that I can substitute to get rid of the current flowing through the battery. Okay? So 1 and 2, and I'm going to substitute to get rid of the current flowing through the battery. Well, what does that mean? I get I25 plus I20 equals I20. And I know the current's 6 and 8 now. That's 7. Good? Okay. Now notice I've eliminated IV, I've eliminated V, and if I compare these two equations, 3 plus 5 and 2 plus 1, okay, notice that I have those two equations, and between the two equations, I have two unknowns. I have I-20, I have I-25. Oh! 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 Never mind, you see another simplification. Let's look at the equation I12. See, these are the kind of things like as I'm going through, I see what I want to do, and then I discover it's, something better. Look at that equation, right? I20 is on one side, and I20 is on the same other side. Yeah, let me write this down. Yeah, let me just write that down. Equation 1 and 2 sub together to eliminate IV. You say, oh, goody, goody. Right? The I-20s cancel out. That guy goes away, that guy goes away. And so what I'm left with is that I-25, well, I guess we already knew this, must be 7 amps. Notice that is the same thing we would have gotten if we had not used junction D, but rather have used junction C. Right? I6 plus I8 must be equal to I25. Okay? So the fact that we didn't use junction C, but we still get the result that we would expect. Okay, sorry, I should have seen that earlier. Well, now that I have I25, let's go back and look at this equation that we got when we had equation 3 and equation 5, and we eliminated the potential of the battery. We know what I25 is. So now we can substitute that in. And we get 24 plus 25 times 7, all divided by 20, is equal to I20. Well, okay, 25 times 7 is 120. Man, this is not a nice number, is it? Right? 25 times 7 is 175, plus 24. So this is 199 over 20. Of course, this is amps equals I20. Okay. So you notice that not always, you don't always get nice numbers. I mean, it would be really nice if that were 200 over 20, but life goes on. Rounded it is, right? Like this is 10 amps. Well, let's go back and look. Of our unknowns, we have now solved for I8. We have now solved for I25. We have now solved for I20. Okay. What's left to solve for, so we've got those three values. What's left to solve for is the current going from the battery and the potential of the battery. So we go back. Let's see here. Well, now that I know I20 and I know I6 and I8, I should be able to find the current coming from the battery. Right? It's just the sum of those three together. The current from the battery is equal to 199 over 20 plus the current flowing through the 6 ohm resistor was 4 amps. The current going through the 8 ohm resistor was 3 amps. And so we have this. Of course, we can find a common denominator. I mean, yeah, you could just plug it into the calculator, but this is 80 plus 60 over 20. So I have no idea what that is. 80 plus 60 is 144 plus 109. So this is 339 over 20 amps is the current coming from the battery. Well, of course, we could go back and a loop rule. This one's probably the easiest, right? The current going through the 20 ohm resistor times 20 ohms is equal to the potential of the battery. So might as well do that one. Of course, that one's nice because I20, so we had 20 I20 is equal to V, but I20 is 199 over 20. And so the 20s cancel and you get 199. Now let's be careful. Potentials are in volts, right? You have an ohm times an amp, and so the final answer is in volts. In fact, I'll label that V battery. And we're done. Okay. We now have solved for all 5 of our unknowns, right? They're all in boxed quantities. 3 amps for the 8 ohm resistor, 7 amps for the 25, almost 10 amps for the 20 ohm resistor. Whatever that value is, so, close to 17, I guess it would be close to 17 amps from the battery, and the battery's at 199 volts. Pretty cool, huh? Okay, I think I'll leave it there for right now. Maybe I'll do another video, whether optional or not, regarding capacitors. But the same idea can be applied to capacitors, KVL and KCL. The only difference being that when dealing with the capacitors, rather than substituting in Ohm's law, okay, that's not what we do anymore. We will substitute in the definition of capacitance. Right? Here's the capacitance, but then we rearrange it so that the potential drop across a capacitor is equal to Q over C. And then you can go on your merry way solving the equations in the same manner. Okay? Well, very good. I think I will leave it there. Of course, more complicated circuits, the equations stay the same. It's just subbing and solving gets more arduous, as you can see here. And like I said, don't get discouraged when you kind of find yourself going down the wrong path. I myself have done it, and I don't realize sometimes that I've got a faster solution in front of my face. So, in any case, apparently it doesn't matter how many letters you have after your last name. These take some time. Okay. Well, thank you for your attention. Keep up the good work. I'll see you next time.